In this video, we're going to digress a little bit and talk about how compilers handle errors, and in particular, what kind of error handling functionality is available in parsers.
A compiler has two relatively distinct jobs. The first is to translate valid programs. That is, if it gets a program from a programmer that is correct, is a valid program, it needs to produce correct code for that program. Now, distinct from that task is the job of giving good feedback for erroneous programs and even just detecting the invalid programs. So we don't want to compile any program that isn't a valid program in the programming language. And programming languages have many different kinds of errors. Here's just a few. So for example, we might have lexical errors using characters that don't even appear in any valid symbol in the language, and these would be detected by the lexical analysis phase. We could have syntax errors, and these would be the parsing errors when all the individual lexical units are correct, but they're assembled in some way that doesn't make sense, and we don't know how to compile it. There could be semantic errors, for example, when types mismatch. Here I've declared x as an integer and used it as a function, and that would be the job of the type checker to catch those. And then, actually, there may be many errors in your program that are not errors of the programming language. The program you wrote is actually a valid program, but it doesn't do what you intended. You actually have a bug in your program. And so while the compiler can detect many kinds of errors, it doesn't detect all of them. And once we get past what the compiler can do, then it's up to testers and users to find the rest of the problems in the programs. So what are the requirements for good error handling? Well, we want the compiler to report errors accurately and clearly so that we can identify what the problem is quickly and fix it. The compiler itself should recover from the error quickly, so when it hits an error, it shouldn't take a long time to make up its mind what to do before proceeding. And finally, we don't want error handling to slow down the compilation of valid code. That is, we shouldn't pay a price for the error handling if we're not really using it. I'm going to talk about three different kinds of error handling. Panic mode and error productions are the two that are used in current compilers. So these are actually things that people use today. Automatic local or global correction is an idea that was pursued extensively in the past, and I think it's historically quite interesting, particularly as a contrast to what people do today, and also why people tried to do it long ago. Panic mode is the simplest and most popular method of error recovery that's widely used. And the basic idea is that when an error is detected, the parser is going to begin discarding tokens until one that has a clear role in the language is found. And then it's going to try to restart itself and continue from that point on. And these tokens, the ones that it's looking for, are called the synchronizing tokens. And these are just tokens that have a well-known role in the language, and so that we can reliably identify where we are. So a typical strategy might be to try to skip to the end of a statement or to the end of a function if an error is found in the statement or function, and then begin parsing either the next statement or the next function. So let's look at a simple hypothetical example of panic mode error recovery. So here's an expression. Clearly it has a problem. We shouldn't have two plus signs in a row, so something's gone wrong here at the second plus. And what's going to happen is the parser is going to come along. The parser is going to be proceeding from left to right. It's going to see the open paren. It's going to see the number 1. It's going to see the plus. Everything is good. And then it's going to see this second plus, and it's not going to know what to do. It's going to realize that it's stuck and that there's no expression in the language that has two plus signs in a row, and it needs to do something to recover. It's encountered a parsing error, and it has to take some error action at this point. So in panic mode recovery, what it's going to do is it's going to hit the panic button. So right at this point, it's going to say, I give up, I'm not parsing normally anymore. It goes into a different mode where it is simply throwing away input until it finds something that it recognizes. And for example, we could say that the policy in for this particular kind of error is to skip ahead to the next integer and then try to continue. So it would just throw away the plus in this case, and then it would restart here at the 2, expecting to see another integer, trying to finish off this expression, and it would treat that as 1 plus 2, and then the parentheses would match, and the rest of the expression would parse just fine. Now, in tools such as Bison, which is a widely used parser generator and one that you may use for the project, there's a special terminal symbol called error to describe how much input to skip. And the productions that are given in Bison look like this. So you would say that the possibilities for E are that E could be an integer, E could be the sum of two E's, two expressions. It could be a parenthesized expression, or if none of these work, okay, so these are the normal productions, right? If none of those work, then we could try some of these productions that have error in them. And error is the special symbol for Bison. And it says, well, these are the alternatives to try if these things over here didn't work. So if you find an error, let's focus on this one right here. So what this says is that if you find an error while you're trying to parse an E, okay, and we haven't actually said how that works yet. We'll see that in future videos. But conceptually, the parser is trying to recognize one of these kinds of expressions here. It's in a state where it thinks it wants to see an integer or a plus or a parenthesized expression. And if that isn't working out, if it gets stuck, well, then it can hit the panic button. It can declare that it's in an error state, and it can throw away all the input. This error will match all the input up to the next integer. And then this whole thing could be counted as an E, as one of these things, and then we would try to continue the parsing. Similarly, if we encounter an error somewhere inside a pair of matched parentheses, well, we could just throw away the whole thing and just reset at the parentheses boundaries and then continue parsing. So these are two possible error recovery strategies if we find an error for this particular kind of symbol in the grammar. And you can have these these productions that involve the error token for as many different kinds of symbols in the language as you like. Another common strategy is to use what are known as error productions. And these specify known common mistakes that programmers make, just as alternative productions in the grammar. So here's a simple example. Let's say we were working on a programming language or a compiler for a programming language that was used by a lot of mathematicians. And instead of writing 5 times x, like computer scientists do, these guys always wanted to write 5 blank x, to just juxtapose the 5 and the x to look more like normal mathematical notation. And they complain that this is always giving them parse errors, that the parser is just complaining over and over again that this is not a well-formed expression. Well, we could just go into our grammar and add a production that made it well-formed. We could just say, well, now it's legal if I have that one kind of expression is just to have 2 expressions that are juxtaposed next to each other with no intervening operator. And this has the disadvantage, obviously, of complicating the grammar. If we do this a lot, our grammar is going to get a lot harder to understand. It's going to be a lot harder to maintain. And essentially all this is doing is promoting common mistakes to alternative syntax. But this is used in practice. People do this sort of thing, and you will see, for example, when you use GCC and other production C compilers, they will often warn you about things you're not supposed to do, but they'll accept them anyway. And this is essentially the mechanism by which they do that. The last strategy I want to talk about a little bit is error correction. So far we've just talked about strategies for detecting errors, but we could also try to fix errors. That is, if the program has mistakes in it, the compiler could try to help the programmer out and say, oh, you obviously didn't mean to write that. Let me try to find a program for you that works. And these kind of corrections, in some sense, we want to find programs that are nearby, programs that aren't too different from the programs that the programmer supplied, but we couldn't compile correctly. And there's a few different things that you can do. 2 of the things that people have tried are things like token insertions and deletions. So here you would like to minimize the edit distance. That would be the metric that you would use to determine whether a program was close to the original program that the programmer supplied. You could also do exhaustive search within some bounds to try all possible programs that are close to the program that was supplied. And there are a couple of disadvantages to this, actually a number of disadvantages. You can imagine that this is hard to implement. It's actually quite complex. This will slow down the parsing of correct programs because we need to keep enough state around that we can manage the search or the editing in the case that we actually do encounter an error. And of course, nearby is not really, it's not really all that clear what that means, and various notions of nearby may or may not actually take us to a program that the programmer would actually be happy with. The best known example of error correction is the compiler PLC. This is a PL1 compiler, that's the PL part, and the C stands for either correction or Cornell, which is where the compiler was built. And PLC is well known for being willing to compile absolutely anything. You could give it the phone book. You can, and people did, give it things like the speech from Hamlet's soliloquy, and it would print out a lot of error messages. Sometimes these error messages would be very funny to read, and it would, in the end, do correction and produce always a valid running PL1 program. And you might ask, why do people bother with that? That doesn't seem, but that may not seem very compelling to us today. And you have to realize that when this work was done back in the 1970s, people lived in a very different world. There was a very slow recompilation cycle. It could take a whole day to get your program to compile and run. You would essentially submit your program in the morning, and you might not get results back until the afternoon. And with that kind of turnaround cycle, even one syntax error in your program was devastating. You could lose a whole day because you mistyped a keyword. And having the compiler try to take a stab at finding a working program for you, if the correction was small and you saved an entire day, if it could fix that one small mistake you made and give you a valid run, that was actually a useful thing to do. And so the goal then was to find as many errors in one cycle as possible. They would try to find as many errors, they try to recover, find as many errors as possible, give you as good feedback as possible so you could fix as many errors, avoid as many retry cycles as possible, and even possibly automatically correct the program so that you could see if the corrections were right, and then possibly the results you got back were useful and enabled you to do even more debugging before the next round. Now, today we're in a completely different situation. We have a very fast, almost interactive recompilation cycle for many projects, and as a result, users generally aren't interested in finding many errors. They tend to correct only one error per cycle. Compilers still report many errors. They'll give you lots and lots of errors, but my observation, certainly my habit personally, and what I see many other people do, is to only fix the first one because it's the most reliable and the one that definitely needs to be fixed before you can try to compile again. If the compilation is fast enough, that's probably the most productive thing to do. And as a result, complex error recovery today is just less compelling than it was a few decades ago.
In this video, we're going to talk about a core data structure used in compilers, the abstract syntax tree.
To briefly review, a parser traces the derivation of a sequence of tokens, but this by itself is not all that useful to a compiler, because the rest of the compiler needs some representation of the program. It needs an actual data structure that tells it what the operations are in the program and how they're put together. Well, we know one such data structure. It's called a parse tree, but it turns out that a parse tree really isn't what we want to work on. Instead, we want to work on something called an abstract syntax tree. And the abstract syntax tree is really just the parse tree, but with some details ignored. We have abstracted away from some of the details of the parse tree. And here's an abbreviation that you'll see. ASTs stand for abstract syntax tree. So let's look at a grammar. Here's the grammar for plus expressions over the integers, and we also have parenthesized expressions. And here's a string. And after lexical analysis, what do we have? Well, we've got a sequence of tokens, again, with their associated lexemes telling us what the actual strings were. And that gets passed into the parser, and then we build a parse tree. And here's a parse tree for that expression. Now, I should stress that this representation, the parse tree, is actually perfectly adequate for compilation. We could do our compiler using the parse tree. This is a faithful representation of the program. The problem is that it would be quite inconvenient to do that. And to see this, let me point out some features of the parse tree. First of all, you can see that the parse tree is quite verbose. So, for example, we have here a node E, and it has only one child. So when there's only one successor of the node, what is that really doing for us? Well, we don't really need the E at all. We could just put the 5 right here and make the tree smaller. And similarly for the other single successor nodes. Furthermore, these parentheses here, well, these are very important in parsing because they show the association of the arguments with respect to these two plus operations. It shows that this plus is nested, this plus down here is nested inside of this plus up here. But once we've done the parsing, the tree structure shows us the same thing. We don't need to know that these were inside of parentheses. The fact that these two expressions are the argument to this plus already tells us all we need to know. And so all of these nodes in here are also in a sense redundant. We don't really need that information anymore. And so what we prefer to do is to use something called an abstract syntax tree that just compresses out all the junk in the parse tree. So here is a abstract syntax tree or a hypothetical abstract syntax tree that would represent the same thing as the parse tree on the previous slide. And you can see here we've really just cut it down to the essential items. We have the 2 plus nodes, we have the 3 arguments, and the association is just shown by which plus node is nested inside the other. We don't have any of the extraneous non-terminals. We don't have the parentheses. Everything is much simpler, and you can imagine that it'll be easier to write algorithms that walk over a structure like this rather than the rather elaborate structure we had on the previous slide. And of course, again, it's called an abstract syntax tree because it abstracts away from the concrete syntax. We suppress details of the concrete syntax and just keep enough information to be able to faithfully represent the program and compile it.
In this video, we're going to talk about our first parsing algorithm, recursive descent parsing.
So recursive descent is what is called a top-down parsing algorithm. And you might suspect that there are also bottom-up parsing algorithms, and there are indeed such things, and we'll be talking about them later. But in a top-down parsing algorithm, the parse tree is constructed from the top, so starting with the root node, and from left to right. And so the terminals then will be seen in the order that they appear in the token stream. So for example, if I have this token stream here, this is a hypothetical parse tree that I could construct, and the numbers here correspond to the order in which the nodes of this parse tree are constructed. So we have to begin at the roots. That's the first thing that happens. And then if T2 belongs here in the parse tree, that'll be the next thing that happens. But then if we have a non-terminal in the next position, that will be number 3. And then if that has children, well, the leftmost one, so because we're going left to right, will be the 4th thing to be generated. And then let's say that the 2 children of number 4 are both terminals, so that will be the next 2 terminals in the input, and so on. The next thing that will happen is the second child of number 3, and then the last 2 terminals appearing in left to right order. So let's consider this grammar for integer expressions. And let's look at a particular input, a very simple one, just open paren 5, close paren. And now what we're going to do is we're going to parse this using a recursive descent strategy. I'm not going to actually show you any pseudocode or anything like that. I'm just going to walk through how this input string would be parsed by using this grammar and the recursive descent algorithm. And the basic idea is that we begin with a non-terminal, begin with the root node, and we always try the rules for a non-terminal in order. So we will begin by starting with e goes to t, and if that doesn't work, we'll try e goes to t plus e. So this is going to be a top-down algorithm beginning at the root. We're going to work from left to right. We try the productions in order, and when the productions fail, we may have to do some backtracking in order to try alternative productions. There are 3 parts. There's the grammar that we're using. There's the parse tree that we're building, and initially that's just the root of the parse tree e. And finally, there's the input that we're processing. And we'll indicate our position in the input, how much of the input we have read by this big fat red arrow, and it always points to the next terminal symbol to be read, the next token to be read. So in this case, we're starting with an open paren. Okay? And also in the grammar, you can see the highlighting here, the brighter red color indicates which production we're going to try. So we're going to begin to build our parse tree by trying the production e goes to t. And what does that mean? Well, that means we make t the child of e, and then we continue trying to build the parse tree. Well, so remember, we're going left to right and top down. So now t is an unexpanded non-terminal. It's the only unexpanded non-terminal, so we have to work on it. And what are we going to do? Well, we're going to try a production for t, and since we haven't tried any yet, we'll just try the first one. T goes to int. So the next step is to make int a child of t, and that's what our parse tree looks like. And now we actually have something that we can check. We can check whether we're making progress. So observe that as long as we're generating non-terminals, we don't really know whether we're on the right track or not. We have no way to check whether the non-terminals that we're generating are going to produce the input string. But once we generate a terminal symbol, then we can compare that with the next input token to see if they're the same. And in this case, unfortunately, they're not. So the int that we generated here doesn't match the open paren in the input. And so clearly, this parsing strategy, or this parse tree that we're building, isn't going to work out. So what we're going to have to do is we're going to have to backtrack. That means we're going to undo one or more of our decisions. We're going to go back to our last decision point and see if there's another alternative to try. So what was the last decision we made? Well, we decided to use t goes to int. So we can undo that, and then we can try the next production for t. And that happens to be t goes to int times t. So we'll expand t using that production. And now, once again, we've generated a terminal in the leftmost position. And so now we're able to compare that with the input. And once again, unfortunately, the int token does not match the open paren, so we have to backtrack again. So we undo that decision. Okay, this takes us back to trying alternatives for t. There's one more possibility, and that's that t goes to open paren e close paren. So we expand t using that production. And now we can compare the token open paren with this open paren with the open paren in the input, and they match. And so that's good. That means that we might be on the right track. And since they match, anything that we do in the future is going to have to match the different input, and so we'll advance the input pointer. So now, what are we going to work on next? Well, we have to expand this non-terminal e, and we're going to do the same thing we did before. We're just going to start with the first production. So we have e goes to t, and then we have to work on t, so we're going to pick the first production for t, and we have t goes to int. And now we can compare it. Is int matching int in the input? And indeed it does, and so we advance the input pointer again. And now we're here, and what's left? Well, we've progressed to this point. We're looking at that open paren, and that also matches. So that matches the input, and now we've matched everything in the parse tree, and our input pointer is at the end of the string. And so this is actually a successful parse of the input expression, of the input string. And so that means that we accept, and the parser terminates successfully.
Welcome back. In this video, I'm going to outline a general algorithm for recursive descent parsing. Before I dive into the details of the recursive descent parsing algorithm, let me just define a couple of small things that we're going to use throughout this video. Token is going to be a type, and we're going to be writing code, and so token will be a type of all the tokens. And the particular tokens that we'll use in the example are things like int open paren, close paren, plus, and times. And so token is a type, and these things are instances, values of that type. And then we're going to need a global variable called next that points to the next token in the input stream. And if you recall from the previous video, we used a big arrow to point into the input to indicate our current position. The global variable next is going to play the same role in our code. So let's begin. The first thing we're going to do is define a number of Boolean functions. And one function we have to define is one that matches a given token in the input. So how does this work? Well, it takes as argument a token, okay, and this is of type token again, and then it just checks whether that matches what's currently pointed to in the input stream. So is TOK equal to the thing pointed by next? And notice that as a side effect, we increment the next pointer. And what's returned then is a Boolean. This is either true or false. So yes, the token that we passed in matches the input, or no, it doesn't. And again, just to stress this, notice that the next pointer is incremented regardless of whether the match succeeded or failed. Now, another thing we need to check for a match of is the nth production of S. So this is a particular production of a particular non-terminal S. And we'll denote that by a function that returns a Boolean, and it's written as S sub n. So this is a function that only checks for the success of one production of S. And I won't write out the code for that now. We'll see that in a minute. And then we're going to need another function that tries all the productions of S. So this one is going to be called just S with no subscript, And so what this one will succeed if any production of S can match the input. All right, so we're going to have two classes of functions for each non-terminal. One class where there's one function per production, and it checks just whether that production can match the input, and then one that combines all the productions for that particular non-terminal together and checks whether any of them can match the input. Okay, that's the general plan. Now let's see how this works for some specific productions. And we'll just use the same grammar that we used in the last video. The first production of that grammar is E goes to T. And now what we want to do is we want to write the functions that are needed to decide whether this production matches some input. And this one happens to be simplicity itself, and it's easy to see why. So first of all, we're writing the function E1. This is the function that deals with the first production for E and returns true only if this production succeeds in matching some input. Well, how would this production match any input? Well, it could only match some input if some production of T matches the input. And we have a name for that function. That's the function T, which tries all the different productions for T. So E1 succeeds, returns true, exactly when T succeeds, returns true. And that's all there is to this first production. For the second production, we have a little more work to do. Now E will succeed if T plus E can match some of the input. And how does that work? Well, first, T has to match some of the input, so some production of T has to match a portion of the input. And after that, we have to find a plus in the input following whatever T matched. And if plus matches, then some production for E has to match some portion of the input. And notice the use of the short-circuiting double AND here. So this is actually important. We're exploiting the semantics of double AND in C and C++, which evaluates the arguments to the double AND in left to right order. So first, T will execute, and notice that T has embedded within it side effects on the pointer into the input. So it's incrementing the next pointer, and it increments it exactly however far T makes it. So whatever T manages to match, the next pointer will advance that far, and when this function returns, it's left pointing to the next terminal that T did not match, and that needs to be a plus, and the call to term will increment the next pointer again, which is exactly where E should pick up, and whatever E can match, it will increment the next pointer just beyond that, so that the rest of the grammar outside of this particular call can match it. And then notice that this particular function is called E2 because this is the function for the second production for E. Well, we have one more thing to deal with for E, and that is the function E itself. We need to write the function that will match any alternative for E. And since there's only these two productions, it just has to match one of these two productions. And this is where the backtracking is dealt with. Now, the only bit of state that we have to worry about in the backtracking is this next pointer. So that needs to be restored if we ever have to undo our decisions. And so the way we accomplish that is we just have a local variable to this function called save that records the position of the next pointer before we do anything. So before we try to match any input, we just remember where the next pointer started when this function was called. Okay? And now to do the alternative matching, we first try E1, and we see if it succeeds. And if it doesn't succeed, well, actually, let's do the succeeds case first. If this succeeds, if this returns true, then the semantics of double OR here means we don't evaluate E2. So this will not be evaluated. The second component here will not be evaluated if E1 returns true. It'll short circuit because it knows that it's going to be true no matter what, and it'll just stop there. And notice that whatever side effects E1 has on the next pointer will be retained, and we'll remember, and when we return true, the next pointer will be left pointing to the next piece of unconsumed input. Now let's consider what happens if E1 returns false. Well, if E1 returns false, well then the only way this OR can be true is if the second component is true. And what's the first thing we do? The first thing we do is restore the next pointer, okay, before we try E2. And if E2 returns true, then the whole thing returns true, and the E function succeeds. If the E function fails, well, then we're out of alternatives for E, and the failure is going to be returned to the next higher level production in our derivation, and it will have to backtrack and try another alternative. Now finally, what about this particular statement, next equals save here? Well, this is not strictly needed. Notice that here we save the next pointer in the save variable, and then the very first thing we do is we copy it back over to next again. This is just for uniformity to make all the productions look the same. But since this is the very first production, we actually don't need this assignment statement if we don't want to have it. So now let's turn our attention to the non-terminal t. There are three productions. The first one is that t goes to int, and that's a simple one to write. We just have to match the terminal int. So the next thing in the input has to be an integer, and if it is, then T1 succeeds. T2 is slightly more complex. That's the production int times t. T goes to int times t. So we have to match an int in the input, followed by a times, followed by something that matches any production of t. The third production is t goes to open paren E close paren. So what has to happen, we have to match an open paren first, and then something that matches one of the productions of E, so we call the function E there, and then finally a close paren. And then putting all three of these together in the function T that tries all three alternatives, we just have exactly the same structure we had for E. So we save the current input pointer, and then we try the alternatives T1, T2, and T3 in order. And at each step, we restore the input pointer before we try the next alternative. To start the parser up, we have to initialize the next pointer to point to the first token in the input stream, and we have to invoke the function that matches anything derivable from the start symbol. So in this case, that's just the function E. And recursive descent parsers are really easy to implement by hand. In fact, people often do implement them by hand in just following the discipline that I showed on the previous slides. To wrap up this video, let's work through a complete example. So here's our grammar, and here is all the code for the recursive descent parser for this grammar. And here is the input that we'll be looking at. And we're going to just mark the next pointer pointing to the initial token of the input. All right, and I'll also draw the parse tree that we're constructing at the same time. So we begin by invoking the start symbol. So we're going to be trying to derive something from E. And the first thing we'll do is we'll try the first production. So we'll try E1. And what does E1 do? E1 is going to try T. It's going to try and derive something from T. So our possible parse tree looks like this. And so we invoke T. And what is T going to do? It's going to try all three productions for T in order. And so it's going to call T1, and we'll see that T1 is going to fail because it's going to try an int. And I won't put it in the parse tree since it isn't going to work, but the int is not going to match the open paren. So that's going to return false, which will cause us to backtrack. It'll reset the input pointer, okay, and to the beginning of the string, and then it'll try T2. And T2 is also going to ask, well, is the input pointer equal to an int? And recall that the term function here always increments the input pointer. So in fact, this pointer is going to move over one token, but this is going to return false because int doesn't match open paren. So we'll come back here. The input pointer will be restored back to the beginning of the string. and then it's going to try the alternative T3. Now when we finally get to T3, something good is going to happen. The first thing it's going to do is going to ask, is the first thing in the input an open paren? And in fact it is. And so the input pointer will advance to point to the int. And then it's going to try to match something derivable from E. So now we have our first recursive call to E. We're back here at E, and it's going to try E1 first and then E2. And so it calls E1, and E1 will only match something if it can match T. Okay, so this is we're down here inside of E now, and then we're going to call T. And what's T going to do? Well, it's going to try all three productions for T in order, the first one of which happens to be the single token int. And that is going to match. It's going to call term int. T1 is calling term int, and that matches the next token in the input stream. So we're happy about that. The input pointer advances again. And now we return through all these levels of calls. T1 succeeds, which means that T succeeds, which means that E succeeds. Okay, and now we're back here in the production for T3, and we're going to ask, well, is the next thing that we see in the input a closed paren? And indeed, it is. And so a closed paren will be recorded. And now T3 will succeed, which means that T succeeds, this T succeeds. And finally, we return to the root call, E, and that returns true, which means that the parse succeeded. That plus the fact that we are now at the end of the input. There's no more input to consume, and we've returned from the start symbol with true, and so we have successfully parsed the input string. In this video, we're going to talk about the main difficulty with recursive descent parsing, a problem known as left recursion. Let's consider a very simple grammar that consists of only one production. S goes to S followed by A. So the recursive descent algorithm for this production is the following. So we just have a function called S1 for the first production of S, and it's going to succeed if the function S succeeds, and then after that succeeds, we see a terminal A in the input stream. And then we have to write a function for the symbol S itself, and since there's only one alternative, there's only one production for S, we don't need to worry about backtracking or anything. So S will succeed exactly when S1 succeeds. There's only one possibility in this case. And now I think you can see the problem. What's going to happen? Well, when we go to parse an input string, we're going to call the function S, which is going to call the function S1. And then what's the function S1 going to do? Well, the very first thing it's going to do is to call the function S again. And as a result, the function S is going to go into an infinite loop, and we're never going to succeed in parsing any input. This will always go into an infinite loop. So the reason that this grammar doesn't behave very well is because it is left recursive. And a left recursive grammar is any grammar that has a non-terminal where if you start with that non-terminal and you do some non-empty sequence of rewrites, notice the plus there, you have to do more than one rewrite. So if you actually do a sequence of replacements, you get back to a situation where you have the same symbol still in the leftmost position. And you can see that this is not going to be good for parsing. So in the case of this grammar up here, what happens? Well, we have S goes to SA, goes to SAA, goes to SAAA, and so on. And we can always get to a situation where we have a long string of A's and an S on the left end of the string. And if we always have an S on the left end of the string, we can never match any input, because the only way we match input is if the first thing we generate is a terminal symbol. But if the first thing is always a non-terminal, we will never make any progress. And it just doesn't work. I mean, recursive descent does not work with left recursive grammars. Well, this seems like a major problem with recursive descent parsing. And it is a problem, but as we'll see shortly, it's really not so major. So let's consider a left recursive grammar of a slightly more general form. So here we have two productions now for s. S goes to s followed by something alpha, or it goes to something else that doesn't mention s, and let's call that beta. And if you think about the language that this generates, it's going to generate all strings that start with a beta and are then followed by any number of alphas. But it does it in a very particular way. So if I write out a derivation here where I use a few, where I use the first production a few times, you can see what's going on. So I get s goes to s followed by alpha, and then s goes to s followed by alpha alpha, and then s goes to s followed by alpha alpha alpha. And if I repeat this, I get s followed by any number of alphas, and then in one more step I can put in beta, and I get beta followed by any number of alphas. So that's the proof that it generates that language, that's the language that begins with a beta and then has some sequence of alphas. But you can see that it does it right to left. It produces the right end of the string first, and in fact the very last thing it produces is the first thing that appears in the input. And that's why it doesn't work with recursive descent parsing, because recursive descent parsing wants to see the first part of the input first and then work left to right. And this grammar is built to produce the string right to left. And therein lies the idea that allows us to fix the problem. So we can generate exactly the same language producing the strings from left to right instead of right to left. And the way we do that is to replace left recursion by right recursion. And this requires us to add one more symbol, in this case, to the grammar. So instead of having s go to something involving s on the left, we'll have s go to beta. So it produces the first thing, notice, in the very first position, and then it goes to s prime. And what does s prime do? Well, s prime produces what you would expect, a sequence of alphas, and it could be the empty sequence. And if you write out an example derivation here, we'll have s goes to beta s prime, which goes to, now using the rules for s prime, goes to beta alpha s prime, goes to beta alpha alpha s prime, goes to, and after any number of rewrites, we get beta followed by some sequence of alphas followed by s prime. And then in one more step, we use the epsilon rule here, and we wind up with beta followed by some number of alphas. And so you can see it generates exactly the same string as the first grammar, but it does so in a right recursive way instead of a left recursive way. So in general, we may have many productions, some of which are left recursive and some of which are not. And the language produced by this particular form of grammar here is going to be all the strings that are derived from s that start with one of the betas, so one of the things here that doesn't involve s, and then it continues with 0 or more instances of the alphas. And we can do exactly the same trick. This is just generalizing the idea that we had before, where we only had one beta and one alpha, to many betas and many alphas. And so the general form of rewriting this left recursive grammar in using right recursion is given here. So here, each of the betas appears as an alternative in the first position. We only need one additional symbol, s prime, and then the s prime rules take care of generating any sequence of the alpha i's. Now, it turns out that that isn't the most general form of left recursion. There are even other ways to encode left recursion in a grammar, and here's another way that's important. So we may have a grammar where nothing is obviously left recursive. So if you look here, you see that the s doesn't even appear on the right-hand side here. And if you look at this production here, a doesn't appear anywhere on the right-hand side. So there's no what's called immediate left recursion in this grammar. But on the other hand, there is left recursion because s goes to a alpha, and then a can go to s beta. And so there we have, in two steps, produce another string with s at the left end. And so this is still a left recursive grammar. We just delayed it by inserting other non-terminals at the leftmost position before we got back to s. So this left recursion can also be eliminated. In fact, this can be eliminated automatically. It doesn't even require human intervention. And if you look at any of the textbooks, particularly in the Dragon book, you'll find algorithms for doing that. So to summarize our discussion of recursive descent parsing, it's a simple and general parsing strategy. You can parse any context-free grammar using recursive descent, so it's very general in that respect. It cannot work with left recursive grammar, so you must eliminate the left recursion. Now, in principle, this can be done automatically. You can have algorithms that will eliminate the left recursion. In practice, people eliminate the left recursion by hand. And the reason for that is that you need to know what the grammar is that you're using so that you can write the semantic actions. And we haven't talked about semantic actions yet, but we will see them shortly. Because you want to know exactly what grammar form the grammar has, people generally do the elimination of left recursion on their own. But that's not difficult to do. And in fact, recursive descent is a popular strategy in practice. There are a lot of the more complicated production compilers, in fact, with complicated grammars, use recursive descent because it is so general. So for example, GCC's front end is a handwritten recursive descent parser.